Hello AP Physics, this is Dunlap, and our topic today is Intro to Forces and Free Body Diagrams. Our learning target is I will describe a force as an interaction between two objects and identify both objects for any force. Go ahead and pause, write that down. Moving on. A force. A force is a push or a pull one object exerts on another object. Forces are important because they can change the motion of an object. In fact, they are the only thing that can change the motion of an object. Two or more objects must interact in order to produce a force. An object cannot exert a force on itself. You must have at least two objects. And we measure forces in newtons, named after Sir Isaac Newton, of course, and the newton is our first derived unit. So the units we've been using so far have been called fundamental units, which is we can't break them down any further. They just are. So, for instance, we've been using meters. We can't break meters down any more than they already are because they are a measure of a fundamental quantity, which is distance or displacement. Seconds we can't break down anymore. It's a fundamental quantity, it's time. And mass is also a fundamental quantity, it's kilograms. So a newton, though, can be broken down into these smaller pieces. And specifically, a newton is a kilogram times meter per second squared. And meter per second squared you should recognize because that's our unit for acceleration. And kilogram you should recognize as mass. So it looks like forces are measured in newtons, and newtons are mass times acceleration. Now we haven't gotten there yet, but I did want to give you a little preview of where we're going with that. If you need to pause, I'm going to switch the slide very soon. So go ahead and pause, write all this down, switching the slide now. Our most common forces are friction. Friction is a force that opposes the direction of motion of an object. Oh God.
Cormisha Hudson to the main office. Cormisha Hudson to the main office.
Awesome. Okay, let's keep going. So friction is a force that opposes the motion of an object, and we have two kinds of friction. We have kinetic friction, the friction that happens if the object is in motion, and static friction, the friction for if an object is standing still, and they're different. Looks like the arrow for friction, there it goes. Okay, so forces are vectors. They have direction and magnitude, so they have a little vector arrow over them. Don't worry too much about kinetic friction and static friction. We are getting there. Second important force, we have tension, and tension is a pulling force exerted by each end of a string, a cable, a chain, or similar one-dimensional, quote-unquote, continuous object. We say a string is one-dimensional. We're going to pretend in physics that it's one-dimensional, that it only has length. We're not worried about its mass, we're not worried about its thickness, we're going to say it's one-dimensional. But in order for a tent to have a tension, there has to be a string or a cable or a chain. Weight is the force due to gravity, and it's equal to the mass of the object times g, the acceleration due to gravity. If an object is on Earth, it will always have weight. Normal force, probably one you haven't heard of, and it's the force perpendicular to the surface of contact. So for instance, I'm sitting here in a stool, and the stool is sitting on the floor. So the reason the stool isn't being pulled through the floor by gravity is because the floor is exerting a normal force back up on the stool. It's balancing out that weight so that the stool doesn't sink through the floor. The floor is exerting a force back up on the stool. And an applied force is the push of one object on another because the pushing object is moving. So for instance, if you push a chair across the floor, you are applying a force to it. You are moving, you are in contact with the chair. That's an applied force. So I've alluded to this so far, but haven't said it. We have two main categories of forces. We have contact forces, which are applied force, tension, and normal force. That's when the two objects are actually touching. And then there are also action at a distance forces. So there's weight, force due to gravity, there's the electric force, and there's the magnetic force. The only one we're really going to worry about right now is weight, force due to gravity. Switching the slide, no. So free body diagrams, just like in the projectile motion, if you can draw the picture and define the variables, you can usually make it through the problem. With force problems, if you can draw the free body diagram and correctly label the forces, you can usually get through the problem. So the rules for free body diagrams are: first, you draw a square representing the object of interest. So for instance, if I said, draw me the free body diagram of a person sitting on a chair, the only object I care about is the person. I don't care about the chair because I said, draw me the free body diagram of the person. So you don't draw a box for the chair, you only draw a box for the person. Then you write the mass, if you have it, of the object inside the square. And last, you draw and label each of the forces acting on the object. And it is important that the tail of the arrow is attached to the square. The arrow always, always, always points away from the box. It doesn't matter that the object, it might be exerting a force on the opposite side of the box. We always have to put the tail of the arrow attached to the square. So let's do an example. I'm going to switch the slide right now.
Alex Ochoa, can you report to the attendance office? Alex Ochoa, please report to the attendance office.
At any rate. So here's our example. We're going to draw the free body diagram for a 2-kilogram kitten sitting on a table. And I want the free body diagram for just the kitten. I don't care about the table. So here is a box that represents the kitten. And we're going to put the mass of the kitten inside. Now the kitten exists on Earth, so it has weight. So let's take, and weight is down. And I'm going to put that with the tail of the arrow attached to the box. And then I'm going to label it weight, lowercase w with an arrow over it because it is a vector. Now, I do know that this kitten is not accelerating downward, so there must be something pushing the kitten back up, and it's the table. The table is pushing the kitten back up. So notice I put that vector on top of the box because we always want the tail to be attached to the box. Even though the table is actually down here, I put the vector up here because we always have to have the arrow pointing away from the box. And then I'm going to label it, and since it's the force due to the table, it's perpendicular to the table, that is the normal force. And this is a very simple free body diagram. We're going to do a million of them in class, but we're going to start simple. So there was my example. That is the end of the notes for now. I think that's it. Thanks for watching, guys. Whoops.